So on to first principles, and the first example is find the derivative of the curve y equals x squared. So that's the derivative of the entire curve. Next example, we'll be finding it at a particular point. But all we want is the equation of the derivative of the curve y equals x squared. And so, the solution. The formula is dy dx, the change in y, over the change in x, which is the gradient, equals the limit as h approaches 0 of f of x plus h minus f of x on x plus h. So we know what f of x is, that's the same as y. F of x is x squared, and f of x plus h, well, anywhere you see an x, you now put an x plus h and do the required operation. So it's x squared plus 2x plus h. So putting that all together, we get dy dx is the limit as h approaches 0 of f of x plus h, which is x squared plus 2xh plus h squared, that's in brackets, minus f of x, which in this case is just x squared. But if there's more than one term in those brackets, the minus will make the entire brackets a different sign, so it's wise to put them in brackets. Okay, and then what you expect is that everything in the numerator without an h in it will cancel out, because then we're going to divide by the h in the denominator. And that's true. So what we've got is the limit as h approaches 0. The x squareds will cancel out, and we've got 2xh plus h squared all over h. And then we're going to divide through by h, or take h out as a common factor. H outside of 2x plus h all over h. So we're left with the limit as h approaches 0 of 2x plus h. Now there's no more discontinuities here. We can sub in the value of the h. So that's 2x plus 0, which means that dy dx for the curve y equals x squared has the equation 2x. This means that any tangent line you draw for the curve y equals x squared at any point will have the equation y equals 2x. And if x is negative, then it's going to be a negative gradient. If x is positive, it'll be a positive gradient. But they all have the equation y equals 2x.